Hi everyone, this is Dr. Paul Kerstetter, and today I want to talk about the simple relaxation oscillator circuit. The circuit is quite handy if you need a square wave oscillator that operates at a specific frequency. In this video, I will describe how the oscillator works, derive the math that predicts its frequency, and show the LTspice simulation. Let's get started. This is the presentation, the relaxation oscillator, a circuit that produces a repetitive square wave output signal. The relaxation oscillator we are going to discuss is shown on the slide. The circuit is composed of two functional blocks, a Schmitt trigger and an AC circuit that charges and discharges. To understand how the circuit works, we will need to dive into the mathematics that describe its behavior. The circuit can be broken down into two topologies. One topology shown in the slide represents a Schmitt trigger in two different states. Because the op-amp has positive feedback, the output can only have two possible states, plus VDD or minus VDD. This means that the node at the positive input has the indicated voltage shown in the slide. Notice in the left diagram that when Vin increases from minus VDD to plus VDD, the switching point for the comparator is VDD divided by 2. This causes the transition to the state shown on the right. When Vin decreases from plus VDD to minus VDD, the switching point is different and becomes minus VDD divided by 2. The presence of different switching points is known as hysteresis, which is shown in the next slide. In the diagram, hysteresis is depicted. Hysteresis means the switching threshold is different depending on the direction of the input voltage. A rising signal switches at a higher threshold, while a falling signal switches at a lower threshold. The biggest reason hysteresis circuits are used is for noise immunity. Hysteresis prevents chatter or rapid switching of the output when the input voltage is near the op-amp switching threshold. For the next part of the analysis, we will focus on the circuit shown on the slide. At the very beginning, when the op-amp supply voltages are turned on, the capacitor has no charge. Because the output voltage is initially railed at plus VDD, the capacitor voltage Vc begins charging at a rate dictated by the resistor R. Eventually, V minus exceeds V plus, causing the op-amp output to switch to its lower rail, minus VDD. Because of this change in the applied voltage across the resistor, the capacitor then begins to discharge. The math describing the capacitor is shown on the slide. The slide illustrates that the current flowing into or out of a capacitor plate is related to the voltage across it by the equation shown. For a positive dV dt, current flows into the positive plate of the capacitor. For a negative dV dt, current flows out of the positive plate. Since the current entering the VC node must equal the current leaving the node, the voltage equation shown on the slide can be derived. This equation is a linear first-order differential equation and has a well-known solution, which is also shown on the slide. As seen from the solution, the voltage Vc starts at minus VDD over 2 at time t equals 0, and then approaches Vout equals VDD over time. In practice, it never actually reaches Vout equals VDD because Vc crosses the V minus threshold first, which causes the op-amp output to switch to a new value, minus VDD. Since we have covered both the hysteresis characteristic and the RC charging characteristic of the circuit, you might ask, what determines the frequency of the oscillation? The derivation used to find the frequency is shown in the slide. Basically, in the equation, the period t is divided by 2 because it represents half of the full period. the portion of time when the capacitor charges from minus VDD to divided by 2 to VDD divided by 2. In the slide, R is equal to 1 k ohm and C is equal to 1 microfarad, which produces a frequency of oscillation of 455 Hz. In this slide, I show what the circuit oscillation looks like. I chose to use the ADA 4620 op amp, which is capable of rail-to-rail output operation. As you can see, it takes about 27 milliseconds for the circuit to start oscillating, but once it does, it oscillates at a frequency of 455 Hz, just like the equations predicted. Well, that's all for now. I hope you enjoyed this video. If you did, please like it and subscribe to the channel. Stay safe, and I'll see you in the next video.